Hello there. Welcome to Empowering the Force. May the course be with you. I'm Mark Tschopp, and I'm going to talk today about neural networks and how you implement them. And I'm going to show that using Excel. So without further ado, I'm going to just dive right in. I guess first, it's snowy outside, so I've got my Boba Fett Christmas sweater on. So there you go, Star Wars fans. But I have learned my lesson because I can see that the green screen is picking up and making me invisible in places. So that's kind of cool. So I got a green background this time. But without further ado, I'm going to go ahead and start to pull up this in Excel. So let's go ahead, pull up Excel. Okay, there we go. And similar to the past, I've kind of blown up the formula bar along the bottom. You can kind of see it highlighted there. The first thing I'll do is just describe the data set. In fact, maybe I can enlarge this just a hair. Okay, so the data set that I'm working on through these neural network examples has 10 input variables, so x1 through x10, that correspond with various parameters that may or may not be important for whether a bullet goes through armor. And then the net result is a 0-1 response, so this is a classification task. And what that response is whether the bullet is stopped or whether the bullet goes through. So just knowing from the past, we've implemented similar things in linear regression and logistic regression. The thickness is going to be important. The velocity is going to be important. But this brings in some other parameters as well into the mix. All of these are already normalized. So an average of 0 and a standard deviation of 1, which is why they look like they're all kind of within the same range. So let's go to our first example. Maybe before we get started, I'll go ahead and blow this up. This is what the neural network looks like. So we have these 10 input nodes. So all shown in yellow. So there's 10 nodes for our 10 input parameters. This is sometimes called the 0th layer of the neural network. So I've kind of shown it off to the side. A0 would be the activations coming out of the 0th layer. So, we've been calling it X1, X2, X3. Here I'm just going to use the terminology of activation, then the layer, so activation in the 0th layer, and then the node within that layer is the _1, the first node, _2, the second node, and so on and so forth. Going back to kind of our schematic, we have one hidden layer, so you see the 2 green nodes there. So we're going to have 2 nodes in the middle in this example, and then one output node in red. So this is a very simple neural network, but it's good to just show the mechanics of how these neural networks work. And again, because we want predictions that are bounded between 0 and 1, we're going to use the sigmoid function for this output node in red. And these green nodes in the middle, we're going to use an activation function there as well. And what we're using here is the hyperbolic tangent. So I'll go ahead and shrink that back up and put it up there in the corner. Just kind of describing this sheet before we go on. And I'm going to spend a little more time on this worksheet, and then we're going to go a little quicker as we scale up the neural network just slightly. But I'll spend a little more time here just so you kind of understand what's going on and the format of these sheets. So again, I've described that these are our 10 input parameters, and here's all our input data. We're going to have weights and biases. We called these thetas when we talked about linear regression and logistic regression. Now we're going to use the neural network terminology, which is weights and bias. You can see the same sort of format. I've got like weight 1 underscore 1. That's weight in the first layer in the first node. Weight 1 underscore 2, weight in the first layer acting on the second node, of the input, and so on and so forth. And then each of these columns are the parameters that are going to go into a node prediction. And then in orange here, here's our middle layer, and then you can see Z2, A2. This is going to be our final output node. So without further ado, let's go ahead and get into it. First thing we're doing is calculating this Z parameter, which is really our our linear regression. So matrix multiplication, and what we want here is we want to select the activations from the previous layer. In this case, it's just our inputs. We want to multiply that by the weights. So I'm going to select all of the weights here. And then I'm going to go ahead and add in the bias. And if we hit enter, that's going to calculate all the values for our data set. Right here we have node 1 and node 2. This is going to be kind of the back half of the node is how I like to think of it. The front half is linear regression. The back half, you apply an activation function to those values. So here we can go ahead and use hyperbolic tangent and then just simply select the dynamic array from the linear regression part. Enter, and there you go. As simple as that. That's the values that are coming out of those green nodes that are going to be propagating forward into the final output node. Let's spend just a little bit more time here. I wanted to also show what does ReLU look like right here. So let's go ahead and delete that. It's easy enough to enter it back in. But if we wanted to do ReLU, remember it's the maximum of 0 and the value. In this case, Z. So max 0, comma, Z. But we can go ahead and select this dynamic array. Actually I showed this just to show that it doesn't work so well, but it gives me an opportunity to introduce a function that actually does work very well with these dynamic arrays and including different activation functions for the neural network. So what it actually did was it took every value within, both of these nodes and simply found the maximum. Now that's not what we want. We wanted it to look at each individual cell and take the maximum of either 0 or that value, which is what it didn't do. Now, the way you can correct this is with a map function. The function itself is just map. We are going to select this, so select an array. We're going to use a lambda function. So the way the lambda function works is first you define the variable, so we'll call it Z. And then we're going to do the function. So the maximum of 0 and Z. Going to close parentheses, close parentheses. I'll keep it there just so everybody gets a good look at what's going on. So it's going to take this array. It's going to take each individual cell within that array. It's going to name it Z and run it through this activation function. So enter. There we go. That would be what ReLU would look like if we actually use that for this neural network. So the interesting part here is, okay, these are positive, 1.9, 0.985, but you see these values here are negative. And so the maximum of those values and 0 is 0. You can see this is negative, and so that ends up being 0. It looks like these values are negative, so these end up being 0. So that's essentially how ReLU, or this rectified linear unit, work as an activation function. And it's very powerful if you have a lot of different layers, a lot of different nodes. It allows you to really model a lot of complex relationships. We're going to go back up here. We're going to select this again. And instead of this ReLU function, we're just going to modify this and put it back in our hyperbolic tangent. So you can see there, hyperbolic tangent. And we're back to where we were with that simpler function, but now we've kind of embedded it within this map function. The reason I chose hyperbolic tangent here is all of these values are already optimized. So I'll kind of take you through this neural network and how optimization works. But I've already went through and actually optimized this with Excel. So we don't need to optimize it again. I'll just show you kind of the mechanics of how that might work. So onto the output node. The output node is going to take the activations from the prior layer. So matrix multiplication. We're going to go ahead and grab this dynamic array with the activation from the prior layer. We're going to multiply that by the weights. We are going to add in the bias. Bam. All this middle one that's Z mod does is I had some trouble with optimization. And so I truncated Z between 30 and negative 30. So if we had really large values or really small values or very large negative values, that it would truncate it at negative 30 to 30. So that's what that is doing. And then finally, since this is the linear regression part, now we need the nonlinear part, which is a sigmoid function. So that's equal to 1 divided by 1 plus the exponential negative 1 times Z. So we're going to take that Z mod. And there we go. There's our predictions. Actually, let me go ahead and cut this. Oops. I'm going to copy this. Copy. Because I wanted to show you something. So right now it's just assuming our prediction is 0 because there's nothing in there. And we have an accuracy of 51%. So that's because 51% of the Y values, are 0. And so just randomly, you would have 51%. But when I go and add back in that sigmoid function for those predictions and look at the accuracy, okay, with a couple nodes in a hidden layer, it brought the accuracy up to 71%. So not bad. Let's go ahead and show how the optimization works. And so again, with optimization, we're going to want a loss function. I'm going to use the let function here just because it's really easy, to bring in. Okay, we want to select all our Y's. Then we have Y hat, and we want to go ahead, go all the way up here to Y hat. I can import that as a dynamic array. So again, that's where that hashtag comes in. Here's the loss. So that's going to be negative Y times log Y hat minus 1 minus Y times log 1 minus Y hat. So this is the binary cross entropy loss function. I'm going to go down to the next line. The last thing you have to enter is what do you want to export back to the spreadsheet. So I want to export that loss back. And there we go. Those are the loss functions for all of our data set. Now, what we have here is we've separated this data set into a training part and a test set. So in order to compute the cost function for the training set and the test set, what we have, we're going to sum the product of, this is our dynamic array of our training set. So there's ones for the ones we want to include and zeros where we don't want to include that. Sum the product of that and the loss function. So there we go. That's only going to sum up the loss functions that we want to include in our training set. And then we want to divide that by the sum of the number of ones in our training set. So this is going to be kind of the average cost function of those. You can see 0.205. Now I just want to drag this across, so I don't want our loss function to change. So I'm just going to put F4, and that's going to keep that stationary. I can drag that across, and you see now if I click on that, it's grabbing the loss functions, it's grabbing the test dynamic array in order to compute that cost function. Here we used regularization, so I used it with the Excel optimizer. So we're going to take this cost function and add a regularizing term. So this regularizing term, again, if you recall, we have a lambda term and we have an L2 term. This L2 term is taking all of these weights. So notice that I grabbed all the weights, but not the bias. So I grabbed all the weights, I squared them, and then I summed them. So that's the kind of L2 summation part. And then our new cost function is going to be equal to this cost function below. And then we're going to add in the lambda times the summa squared of all the weights. And this would be the objective function right here that you would take and insert into your optimization. And so you're going to say minimize that cost function while modifying, you see the bias and weights for all of the layers. So it's going to take all of those parameters and modify them. So that's how that works. Again, you can test out different lambda values and select the one that best gives you the lowest cost function for the test set if you want. Actually, in some of these cases, it's better to break it into training, validation, and a test set, as I've talked about in some other videos. So here, this was fairly good, gave some regularization to the model, so that's what I used here. Let's go back to let's look at the color coding here. So I hadn't talked about it yet. But what you're actually seeing is this color coding of which of these weights, is the model preferring, over others. So because I've normalized these inputs, these weights actually give you a clue as to which of these input parameters is more important in making the predictions from this model. So you can see here this first node. If you look just at the weights, it's focusing on the thickness and the velocity. So those are kind of two important parameters and much less so on the rest of the parameters. In this second node, so again, you're talking about the second green node over here. It really focuses on the velocity, focuses a little bit on all these other parameters as well. So it gives you an indication that node 1 focuses on 1 and 3 in terms of our input parameters, whereas node 2 focuses more so on 3 and a few others as well. But when you get to the output node, again, you're going to do the same thing. So if you're going to try to track the logic of what the model finds important in making good predictions, negative 4.6, a higher magnitude than this positive one. So it's really focusing on node 1 from the layer before. So you go back to node 1, and node 1 was focusing on thickness and velocity. So it gives you some indication. You can sort of track the logic when there's very few layers and very few nodes. However, in most of these neural networks, you're going to expand the nodes drastically in these hidden layers and expand the number of hidden layers. And so it becomes more and more difficult to really trace how each individual input is impacting the output. But by colorizing things here with the conditional formatting, again, you can drag it down, and use that to colorize things. It gives you some indication of what the model is focusing on. So let's go ahead and go to our next one. What we have here, I'll blow it up. The only thing that's really changed is we've added a few more nodes in this first hidden layer. So that's really what's changed. Because we've explained a lot in the first example, I'm really just going to run through it. So matrix multiplication, again, x, and then we're going to choose all of our weights, and then we're going to add in the bias. We're going to, once again, use this map function. So we're going to grab all these z's, use the lambda function to identify z, and then the activation function is that hyperbolic tangent. So you can see there. Now we're already on to the second layer, or this output node. And again, this is a matrix multiplication of the activations coming out of the prior layer times the weights. You can see now there's 4 weights because we had 4 nodes in that hidden layer. And then we're going to add in the bias. And then y hat is simply going to be 1 divided by 1 plus the exponential negative 1 times z. And there we go. There's our predictions. I can kind of scroll over a little bit. You see we had 71% for the last model. As we added a few more nodes, we now have 80%. I'm not going to go through the loss and the optimization. That stays the same for this model. But let's track it backwards again. Let's look at this output node. So here's the weights associated with it. A large negative weight or a large magnitude for this first, focusing on this first node of the hidden layer. So this large magnitude is associated with all these weights within that first node of that hidden layer. And what does that first node of the hidden layer focus on? Well, it focuses on the thickness and the velocity. So once again, we're seeing a sort of trend here with how the neural network model and what it's focusing on in order to make a good prediction. But that's not the only thing. You can see that there's some focus on the second node, which focuses on velocity, a few other of these bullet parameters. This third one doesn't really focus on anything, and so this weight would indicate that it doesn't pay a whole lot of attention to that in terms of making a prediction. So that's kind of how you could read into some of these weights within the model. And this last one, let me go over here. Yep, there's a schematic. So now we're going to actually add 2 hidden layers. So we have this hidden layer. This would be the first layer, right? Because the yellow would be the 0th layer. So this is the first layer, second layer, and then the third layer is our output node. I'm actually just going to push that over to the side here, and we're going to run through this as well. So this is very similar to what we did in the last layers. So there are our x's. We're going to select all the weights, and then we're going to add in the bias. Enter. We're going to use this map function. We're going to grab the z's. Lambda, z, hyperbolic tangent of z, close parentheses, and there we can see everything. Okay, now we have the activations coming out of the 4 nodes of that first layer. So let's go ahead and advance over. So this second hidden layer is just matrix multiplication. Again, it's going to take the activations from the layer just prior to that. It's going to multiply it by the weights, and it's going to add in the bias. Then you have to apply the activation function. So it's equal. We're going to use the map function again. I just like to stay consistent. Lambda of z, then enter your activation function, which is the hyperbolic tangent of z, enter, and there's our dynamic array. So those are all the activations coming out of the 2 nodes in that second layer. And then finally, we have the output layer, which is going to be the matrix multiplication of the activations coming out of that second layer times the weights plus the bias. And then here we go. We have y hat, or our prediction of y. It's going to be equal, and we're going to use a sigmoid function. So 1 plus the exponential -1 times z. Hashtag to capture the whole dynamic array. Enter. And there's our predictions. If we kind of scroll over a little bit, yeah, here's the accuracy, 84%. So it got a little bit better by adding a few more nodes and, another hidden layer, and that allowed the model to capture a little bit more. In reality, some of this may be overfit. There's different techniques to try to regularize your models and keep them from overfitting. Sometimes when you have high values within your model, that might lead you to believe that it's overfitting. I'm not quite sure if I threw this into Python, would I get drastically different results or not. I do know that the accuracy could probably be pushed up a little higher, I would imagine. But again, there's some shots where the velocity, thickness, there's some variability in the output. And so you might not be able to capture absolutely everything. So with that kind of just led you through the mechanics of how these neural networks work. So let's go ahead and I'll go back to the intro screen. So I hope you've learned something about how these neural networks work. I mean, what I think is really powerful here is that you see just how simple these interior nodes are. It's matrix multiplication, which is the linear regression part. So I like to think of these nodes as almost split into 2 parts. One part that's linear regression, and then a second part that's going to have your activation function. So that's going to have this nonlinear function. I used hyperbolic tangent here. I showed how you would implement something like the rectified linear unit or ReLU. Either one of those would work and are very simple to implement. And really the power of capturing these complex relationships comes through, you can use these simple functions over and over and over again. And as you expand the number of hidden layers, as you expand the number of nodes, you're going to get better and better approximations of what the true function and true relationship is. So with that, I'm going to leave you here. I hope that this has been helpful, and may the course be with you.